All right. So I got it working on the one screen. Are you guys seeing it yet? It's not showing up on my monitor that you guys are seeing it. So uh, I'm going to go ahead and get started with the lecture, assuming that you guys are able to see. And, certainly let me know if something's not going right. So here's just starting with the announcements as usual. Of course, you've seen most of them already. The grader has not advanced the grading of homework 7. So I hope to be spending some time this evening to try and bring that forward. I know you got a couple of ungraded homeworks that you would like to have assessed, and soon. The last homework assignment will go out hopefully today. However, I'm going to make that last homework assignment optional, meaning it's not going to be graded. It's essentially for practice only. The solutions to the problem set will be posted at the same time as the problem set. That's because I know everybody's busy, and we've had a busy couple weeks. It's been hard to get out problem sets, get them graded, and get them done on your end and get them back. So I think this will be a reasonable balance of making sure that we have all the necessary content having been practiced for the exam, but without adding undue stress to you guys as students. I know it's a tough time of year. It's an especially tough year just in general. And don't forget, of course, we're coming up not too far away from the due date for the finite element project. So let me know how that's going. I did spend a full day of office hours today. I've had students in and out of that office hours, but surprisingly few from this class in terms of the number of students who participated from this class. I guess I'm going to hope that that means that you guys are doing well on this project, and that everything's going pretty smoothly for you. If not, there's not going to be too many more opportunities for office hours. I will take office hours appointments by appointment, really at any time that you guys would like to make a request. If I can fit you in, I'll do my best to fit you in. I know that Tuesdays and Thursdays during office hours maybe works during the semester. A little bit tougher this time of year for you to get all your content covered in that period. So, if you can't make Tuesday or Thursday at 11, there's not too many Tuesdays or Thursdays left. So shoot me an email. We'll schedule some time and try and get you helped out. Okay, so we're going to pick up where we left off with energy methods. And a reminder of where we ended up. We ended up at this concept of virtual work. Okay, and basically what we described was this really important concept, and I will I'll start right here at this slide. This idea that there was this thing called virtual work, which was related to something that we're going to call a virtual displacement. Okay, these two words, work and displacement, when we put the word virtual in front of them, we're indicating that we have it is something different than work in the traditional sense that you're used to. It is, in some sense, a pretend work, really, is what it is. We call it virtual. And what we're going to do is we're going to assume that you start with some structure that's under load. Let's say an aircraft wing. You're flying along in the aircraft wing is loaded, obviously, from the loads of flight, typically aerodynamic loads. We'll describe it mostly the lifting load. So you've got this lifting load on the wing. The wing, because it is an elastic structure, it's not rigid, it deforms. So it's got a combination of load present and deflection or deformation that's present. Now, this idea of virtual work is we take whatever that current deflection is, what I'm going to generally call the actual displacement or the real displacement, and we're going to superimpose on that displacement some small perturbation of the displacement. So it's a small increment of work, but that is an arbitrary imagined displacement. Now, for whatever reason, my monitoring computer has been kicked off. again, so I don't know if you are able to hear me. Okay, flipping back to the screen, you guys are still there, so let me bring that other computer back up. It's Windows. You guys shouldn't use Windows. You should use Linux. It's much more reliable. Okay, so that's coming back up. Anyway, so again, a real displacement exists, real forces exist. We're now going to superimpose on those forces an imaginary displacement, a virtual displacement, a small increment of displacement that we don't know its value. We just know that it could exist theoretically. Now, we put some limits on what type of displacement could exist. We said it had to be kinematically admissible. And, I know there was a question about that during the last lecture. In summary, that displacement cannot violate boundary conditions, specifically kinematic boundary conditions. So these are things like displacements at boundaries or rotations at boundaries or something that would be similar. And here, this is really important. This, even though we're assuming it can exist, we don't know what it is. It's in fact arbitrary. It could be any small increment of displacement that we would superimpose on the load that the structure, or on the deformation that the structure actually has, the real displacement. Okay, so that's what we described. And now we also said, well, if you can imagine that, if you can twist your brain around in circles a little bit to imagine that there might be something other than the real solution in displacement field, we might also accept that there could be some other displacement field or force field that would be a small change from the existing real force field. So we called that a virtual force. And again, we said that this could be any arbitrary force that ultimately goes to zero on the boundaries. That means it can't violate any externally applied loads. But internally, we could assume that it would vary to some degree. Anyway, so we described now two things, really a virtual displacement, the one we think of more often, but then in concept also this idea of a virtual force. And then the final statement was the principle of virtual work. And if you take away one concept, just a concept from this class, it would be really a great concept to take away, is that this idea of the principle of virtual work, a system in static equilibrium. In fact, it is in static equilibrium if and only if the virtual work is zero for all independent virtual displacements. Now, I know that that's a lot to chew on. I know that's not really clear just by description. We need to go through and do examples for you to grasp that. Anyway, the equation is this simple. Delta W is equal to 0. So in order to really internalize this concept, I think it's really critical we go through and do a couple of examples. I'm seeing one or two things come across the chat window. Let me check that real quickly. Again, that monitor is not coming through great. Ethan, I saw the question was from you. Maybe you could just speak the question.
Yeah, so on Tuesday you were talking about the illusory force Q applied at the midpoint of the beam. I was just wondering if that's an example of a virtual force or if that's an entirely unrelated phenomenon.
That's a great question, Ethan, and actually this is, believe it or not, an unrelated phenomenon. So we were not at the time applying the principle of virtual work in that calculation. So this is a somewhat different description of an imaginary force. Now, we in that context, we imagined a force to exist and then said it was equal to 0 at the end of our pretend. Okay, in this example where we're doing virtual work, we imagine a virtual force to exist, but then we don't pretend that it's equal to 0. So there is a difference between these two things. Okay, anyway, so here, let's go through an example so you guys get a picture of what's going on. So here I'm drawing a very simplistic structure. Basically, this is a hinged two teeter-totters work together in some sense. So they're hinged at the middle. and they are balanced across pivot points, and we've got a spring placed also at the middle. So, this is the idea. The teeter-totters can swing about their pivot points, and the thing that restrains them from swinging is a spring. The spring is going to have a spring constant K, and what we're going to do in this problem is we're going to apply two forces, one called P and one called Q, in opposite directions on the opposite ends of these teeter-totters. Okay, we're going to do this as a rigid body problem. So we're essentially, in doing so, stating that all the energy that's stored in the system is stored in the spring. The teeter-totters themselves are rigid enough that they don't store any elastic energy and that there's no deformation of them other than rigid body motion. Okay, now another thing to look at here is to say, okay, since we're not really treating this as an energy method, we could just also sort of highlight that at this point where the spring is applied, there is an amount of deflection that will occur, and then there's going to be a resulting spring reaction force. And so we're really going to treat this as a problem that is one of this reaction force. Okay, now I got kicked out of my monitoring computer again, so for the time being, if you have a question, just chime in and interrupt me, and I'm happy to take it. Sorry that that's not working very well right now. Okay, so here's the key. The key here is we're going to apply this principle of virtual work. Okay, and the principle of virtual work was as simple as writing this expression. The virtual work is equal to 0. Now, nothing's ever quite that simple. So really what we need to now do is calculate components of virtual work relative to some degrees of freedom that are in the problem. Okay, so pretend for the second that this thing has actually deformed. These loads exist, and the teeter-totter is deforming as shown. So there is this deformation. We're going to use the only degree of freedom in the problem is going to be this angle theta. And, because of the distances involved, the pivots are each at the distance L/2 from the point of application of the spring. And they are, basically this is a symmetric teeter-totter. So that this angle theta is going to be the same as this angle theta over here. Okay, now, as I described previously, we know that this thing is deflected, so it's at some position theta. And now we're going to superimpose on that some calculation of virtual work. So in order to do that, we need to first identify, well, what is the current position of this point where the load is applied, Q? Okay, and similarly, what is the current position of this point where the load is applied, P? Okay, so step one, if you're following a recipe for doing these problems, is describe the current position of these forces. Really, three forces present here, P, Q, and then the spring force K. Okay, so at the position for the Y value of the position P, since it is a distance L/2 from the pivot point, and it's at an angle theta relative to that point, or I should say actually the teeter-totter itself has a distance L/2, right? So the actual Y position can be relatively easily described as being at a positive location, L times sine theta over 2, really L/2 sine theta. And similarly, we can look at the current position of this force P and the point that it is applied to. Again, its distance is L/2. Again, its angle is theta. So we can say for Q, Again, it's going in the positive y direction, the magnitude L over 2 sine theta. The current position of the point associated with the force on the spring is quite similar, but of course it's in the opposite direction. So that one we're going to say is equal to minus L over 2 sine of theta. All right, just jumping back and forth. Now I'm going to have to jump back and forth just to monitor that chat window. Okay. All right, is everybody kind of comfortable with this idea of where these forces are being applied, their current locations? Pretty simple, right? Okay. Now, the next thing is we need to imagine that we're going to have a superposition. We're going to add on to the current degree of freedom. The current degree of freedom theta describes those positions. Now we're going to imagine that something besides theta could have occurred. This process mathematically is called taking the variation. Okay, it's kind of like taking a derivative in some sense. And if you take the advanced level course in the spring that's offered called Foundations of Structural Mechanics, we'll go into the details of this mathematics a little bit more. But what we're essentially saying is if we had theta, we can assume that there's some little change delta theta. And that little change delta theta is essentially like taking a derivative. So mathematically, it ends up being, in fact, very similar to taking a derivative. We're going to take the variation of the position P, and it's going to be equal to now what amounts to the variation of the description of that position. So, and like I say, this is very similar to taking a derivative. So the derivative of sine is cosine. So in practice, the variation would be cosine theta d theta. Okay, and you know, again, if we were, I'm going to do this as if it were a derivative, so you can see it. Now recognize it's slightly different. Okay, dyp d theta is going to be equal to L cosine of theta over 2. And then, you know, you can theoretically, you can move this over. That's if you were taking the derivative. Now, this is not exactly the same as taking the derivative, but mathematically it acts very similarly. So now instead of calling this a derivative, we're calling this a variation. It is we're admitting a small change in the angle theta. Okay, now, by the way, this symbol here, this delta symbol, is the symbol for variation. Okay, note that's a little bit different than partial derivative or full derivative. So, you know, keep in mind this is not identically equal to those operations, but it's quite similar. Okay, so anyway, we take the variation of the position yp. We take the variation of the position yk, we take the variation of the position yq, and we get, in all cases, L over 2 cosine theta d theta with either a positive or a negative sign. Okay, so the next thing that we're going to do is we're going to write the virtual work associated with this virtual displacement. Okay, that small increment of theta, this thing that we're now calling delta theta, is a small increment in theta. It's like a derivative. Okay, so this small increment in theta, when applied to the force that's present at that location, you know, we've got a force there, we've got an imagined displacement, gives a contribution to virtual work. So delta W is going to be equal to delta YQ times FQ plus delta YP times FP plus delta YK times FK. Okay, and you know, just applying this into our calculation, it's pretty simple. You know, I'm just multiplying those values by force now. Okay, now the way I wrote this equation, I wrote it as if all of these forces were acting in a positive direction. That's just for consistency, you know, it's nice to always know that positive in the positive direction is positive, right? So I wrote FQ and FK and FP as if they were all positive. Now I need to go back and substitute the fact that FP is actually minus P, FQ is actually plus Q, and FK is actually minus K, YK. Okay, so here I'm going to substitute these forces in, this one, and this one. And so since we knew what YK was originally, this was the actual displacement, I can then sub that in as well. So FK is now LK sine of theta over 2. Okay, so now plugging those into the equation and simplifying, note that in each case we have a cosine theta over 2. So here's a cosine theta over 2, here's a cosine theta over 2, here's a cosine theta over 2. I'm going to collect terms, so there's cosine theta over 2. There's an L in all of these terms, so here's my L. I've made my substitution. What we now have is Q minus P minus LK sine theta over 2 delta theta. And we know that because this is virtual work, this has to be equal to 0. Okay, so what do we do next? What's the logical thing to do? Well, so here's what we're actually going to do. We're going to recognize that this value delta theta is arbitrary, okay? And that might actually have some serious implications. But before I go into that step, you might have the temptation to say, well, okay, if all of this, oops, cancel, hold on. If all of this term were equal to 0, well, if I'm solving for 0, why don't I just declare that this delta theta is equal to 0? Okay, and if I did that, then my equation is automatically satisfied. Well, that is actually going to be a violation of the fact that this is arbitrary. Okay, so delta theta cannot be equal to 0. If you go back a few slides, I'll bring it back up for a minute here. This displacement is arbitrary. If it were equal to 0, it's not arbitrary. It could theoretically be equal to 0, but it could be equal to 1, it could be equal to pi, it could be equal to any magnitude, really any small magnitude. So therefore, we cannot use this idea that delta theta is equal to 0 to solve this problem. Okay, so we're going to have to do something else. So then what we know is that the delta theta, we could divide by delta theta, and then what we have left is this, and in fact we could divide by L cosine theta over 2, and what we have left is this. Okay, well, before I do that, I can also recognize that we can use a small angle approximation if we would so choose, and say that sine of theta is equal to theta and cosine of theta is equal to 1. So I can cancel the L cosine theta over to the right-hand side by dividing by those, and then I can make this substitution. Sine of theta is approximately equal to theta, and now that resides in here. And I can then further solve this problem for theta. This is the original displacement. Theta is now going to be equal to this magnitude, 2 times Q minus P over L over K. All right, so I I'm feeling emotionally like this is a little clumsy to do in the way that I'm doing it. This is the first time I've ever tried to present this online with slides. So the presentation doesn't feel great to me, but I think and I hope that the point comes across. Let me try and summarize the point for you. Okay, again, we assumed some reasonable deflection to occur. We called it theta, we didn't know what it was. Then we took this sort of mental leap and we said, all right, well, I'm going to imagine an additional displacement to occur, or rotation in this case. And by doing so, by imagining something that is not present, we actually loop back and are able to calculate the original angle, theta. And I think that's actually really incredible. It's pretty cool. I don't know about you guys, but I think that's cool. And it's also a bit of an emotional mental leap. How are we using this tool? We're pretending that something doesn't, or we're pretending something exists. And by making that pretend statement, we can actually calculate what really exists. It's very strange. I'm hoping to get a few questions across because I don't know, given this online presentation, this is one of the more difficult concepts, I think, to convey, and I'm hoping that if there is some confusion about it, that you guys are going to be willing to stand up and ask those questions now. I do have the monitor back up again, but I'm not entirely sure whether it's working. David, I see you waving at me. That probably was not a question, right? That was just indicating that things are working. Okay, good. Are you guys okay with this concept? All right, well, it sounds like you are. Good.
Could you go over the part where you do the displacements again, or no, the variation?
Yeah. So here is that variation. Okay. And mathematically, as I said, mathematically, this is like taking a derivative. So let me start here. If we took the derivative, full derivative of yp, dyp is going to be equal to L cosine theta d theta over 2. Okay, that's if we took a derivative. Now, what is a derivative? A derivative, functionally, mathematically, what is it? It is a measure of a small increment in one thing creating a small increment in another. A small increment in one thing creating a small increment in another. So derivative dyp of theta is equal to L sine of theta d theta over 2. Typically, we then divide by d theta and say it's and then say that that's the magnitude dy d theta. Okay, that's functionally what happens with a derivative. For this idea of taking the variation, well, I guess I should briefly introduce what's different between variations and derivatives. Okay, this will be covered much more extensively in the advanced structural mechanics class, but the idea is that when you're taking derivatives, you're taking you're assessing changes in functions as a result of changes in variables. So if I change theta, the function on the right-hand side, and then I change theta, which is a variable, then I'm assessing how much change that it's created. That's called a derivative. Now, there are times where the right-hand side becomes a function of a function. Okay, so instead of calling that a function, we call that a functional. A functional is an equation that has functions of functions within it. And so the variation is the conceptual idea of taking derivatives of functionals. So taking derivatives of functions of functions. Okay, so it's one step past the simple concept of a derivative. But for most of the problems that we're doing, these functions will be functions of variables, and so it's mathematically identical. Okay. So anyway, that's how we got from here to here. And then by taking that derivative, we can calculate work. This is how much work occurs if we have a small change in that displacement. And then from that, we go through and say, okay, we now can compute the actual displacement using the, in some sense, imagined perturbation of displacement. Does that help, Nicole?
Yeah, thank you.
Okay. So, as with all things in life, it's good idea to have a sanity check on this answer. Let's go back to the problem statement here. So if we had this teeter-totter, and there was actually a spring present on the teeter-totter, let's just, for the sake of, before I give a sanity check, anybody else like to offer a sanity check? All right. Well, I don't want to wait for too long. I know you guys tend to not necessarily want to speak up, but here we go. So let's do a sanity check. Let's assume, for the sake of argument, that the magnitude of Q was actually 0. So we can just basically take Q away. Since the right-hand side is a rigid body, it's not contributing anything to the energy stored. It actually essentially becomes irrelevant to the problem. And so we would need to then calculate the associated deflection with the point force restrained by a spring. And you go through and you do this calculation. So if Q is equal to 0, the magnitude of theta would be equal to basically the spring force. The spring force has to balance out P, and in order to get a sufficient amount of spring force to balance P, we would need it to deflect an amount that gives that force, and that magnitude works itself out. It would be, what is a spring force? So the distance is L over 2. If we look at how much deflection occurs with L over 2 times theta, we would end up with this 2 over LK times P, and it would work itself out. Anyway, think through that. Again, this is one of those things that's kind of clumsy when I'm trying to do this online rather than in person writing on the board. So I apologize if that is at all confusing, but go through and mentally check that at home after lecture is over. Okay, so there we did a rigid body example. It's a fairly easy, simplistic, single degree of freedom problem. Now, what the beauty part about single degree of freedom problems is there's only one variable that we need to assess for having this small perturbation in that variable. Okay, the reality is that most of the world is not made up of discrete systems with one variable in them. Okay, most structures in the world, if not all, that are real structures have many degrees of freedom associated with them. Okay, and so we need to be able to generalize this concept to having many degrees of freedom. And furthermore, we need to ideally be able to generalize this to a structure that has an infinite number of degrees of freedom. So at each point in a deformable structure, you can get a unique displacement field. And so that's in some ways an infinite number of degrees of freedom that you need to check. So now let's do another example where we compute now the principle of virtual work. We're taking this little increment of work that occurs, but except now we're going to do it on a deformable body. Okay, now in this context, I'm going to write the equation this way. It's the same equation really, but I want you to capture this as a mechanism for it, no different than previously. So increments of work in each of the X, Y, and Z directions can be written in terms of a summation. So what's in here is sigma ij delta epsilon ij. Okay, we have a set of internal forces that are present. By analogy, we had the single discrete, actually two of them, discrete external forces. And at each of those external forces, we now allowed a increment of displacement to occur. Now, if we have a deformable body, the analog to force in a deformable body internal forces is stress, and the analog to displacement for an internal body is strain. So now we have stress times the increment variation of strain, right? This incremental small change in strain, that gives us an incremental amount of work that's done internally within the structure. And of course, the total virtual work is the sum of all those incremental virtual works within the body. So we're integrating over the volume, dV. All right, I hope that's clear. Again, so this, we're going to call this the virtual internal work, is the work associated with the deformation internally to the structure, a variation of it, or also called a virtual displacement internally, times the internal stresses that are present. Of course, we still have external work. These, by example, are the forces that we looked at in the last problem, or really any virtual or any external forces that would be present. We can have associated external virtual displacements, and so those would contribute external virtual work. Okay, now some notes to think about when you're thinking about a deformable body like this. A reaction force at a restrained support does not do work. Okay, so what do I mean by this? If here if we had an axial load carrying member, okay, we recognize that there is a constraint here, so there's no deformation. Even though there is a force there that's required to hold that in place, because there's no deformation, there's no work. So that's just one thing to note in our description here. Okay, so the other idea that's kind of an important takeaway from this is that notice in our derivation, we have not described in any way the constitutive equation. So most of the stuff we do in this class is linear elastic material properties, and certainly this idea of virtual work applies for linear elastic materials. But if we had materials that were not linear or were not elastic for that matter, this principle of virtual work actually still applies. Okay, now here is our, so I'm going to kind of blend two concepts together a little bit, and we're doing this in this course because they are very related. Again, I really encourage you guys to consider taking the advanced structural mechanics course that'll be taught in the spring, where we're going to differentiate these concepts a little bit more. But the one that we're going to now bring in is called the minimum potential energy method. Okay, now this is similar to virtual work. In fact, it's based in some ways on virtual work, but now we're going to describe it for materials that do not dissipate energy. So now we're going to limit our work to the context of linear elastic materials. Okay, so an analogous statement for virtual work now is going to be this idea of minimum potential energy. So you guys probably have seen this equation before. That is potential energy represented by the symbol pi, capital Pi, is going to be equal to, it's going to be equal to the internal strain energy minus the external work. And we're going to say that the external work is going to be described as the potential of the external loads. So this is a potential field. We're going to call that plus W. I'm sorry, plus V. So U minus W is equivalent to U plus V, where now the only difference is external work or potential of external loads, different verbal description of them, different mathematical representation of them, but really it's only a sign change. Okay, now, and this ultimately, this is very related to the principle of virtual work. The next thing we're going to do is we're going to take this variation and say that it's going to be equal to 0. Okay, again, the virtual work will be 0 for all these virtual displacements that occur. And so any small increment, any change to the potential energy that's present must be equal to 0 as we imagine changes to the degrees of freedom that are present. So Nicole in the chat window has asked, what are U and V again? So U is the strain energy. That one we derived several lectures ago. I'll just stop there because it takes me too long to write it. But if you recall, so this was the integral of stress destrain, right? And then integrate that over the volume. So that's what U is. And V is just minus W. That's the potential of the external loads. And of course, you remember that, this is in the context of a force being equal to, something that is minus dV di, where I is a direction, right? So this is what we called, this is our definition of what a potential field was. And so as you are doing external work, that's describable as a potential field. And so we're just putting a positive sign on this and putting it here. Okay, so the total potential energy, this is the sum of the external work potential and the internal strain energy potential, can be described as a function. And in this case, it's a function of multiple variables, Q1, Q2, all the way up to Qn, potentially as many as an infinite number of degrees of freedom. And the variation of that, then again, this is very similar to taking a derivative, not exactly the same thing, but very similar. Functions of functions, it's a functional, okay? In fact, let me go ahead and make that very clear. So I said that U is equal to the integral of stress destrain. Okay, stress and strain themselves are functions of displacement. Okay, so this U is a function of functions called a functional. And then in order to conceptually take the derivative, we mathematically do this thing called taking the variation. So it's, and again, we're going to get into the details of that more in the advanced structural mechanics class. Anyway, functionally, this works out to be equal to the following. It's, again, similar to a derivative. Partial pi, partial qi times delta qi plus partial pi, partial q2, delta q2, and then theoretically this could go on forever. Expressed in a relatively shorthand notation, the variation is equal to the sum over all the degrees of freedom of the derivative of pi with respect to a degree of freedom times the variation with respect to that degree of freedom. All right, now keep in mind what these perturbations are. So delta qi now is a virtual displacement. It is some small increment that we're admitting over and above the actual displacement. Okay, two things that are important. It's number one, arbitrary. We don't know precisely its magnitude. And number two, it has to be kinematically admissible. Okay, that means it can't violate boundary conditions. So arbitrary without violating boundary conditions. Now, why does this matter? If we go back to this equation, what we see here, first let me deal with the fact that it is arbitrary and independent. Okay, so if it's arbitrary, I can't use Q1 to cancel anything to do with Q2 because we don't know what Q1 is. We don't know what Q2 is. In fact, we can't say they are functions of each other. These are independent and arbitrary functions. So this can't cancel this. That means this in and of itself must be 0. And this in and of itself must also be 0. If, on the other hand, let me do a counter example to that. If I could say that Q1 and Q2 are the same, then somehow I could use this derivative to cancel this derivative. But that's not what's happening here. Q1 and Q2 are independent and arbitrary, so I can't use these terms to cancel these terms. So ultimately, this equation becomes a whole series of equations. Okay, so these are now independent equations. Delta pi, delta qi, delta q is equal to 0, and we have n of them. All right, I know that this is a bit hairy the first time you hear it, and again, I'm a little concerned this doesn't come over very well in a presentation without writing on a chalkboard because I've not done it this way. Are you guys on board with me? Is this something that you guys can wrap your brains around? All right, I saw a couple of thumbs up, and I see pencils still flying. Let me know if I'm going too quickly. Okay, so bottom line, we have n equations, potentially as many as infinity equations here. Now, we've introduced the mathematics of it. Now I want to solidify the concept for you by doing a deformable body example. Okay, what I have is an axially loaded structure. In fact, it's two components combined together. We have, we'll say, a relatively thin one, which we're going to call subsegment 1. We're going to have subsegment 2. They can theoretically have different materials, but we're going to say that those two segments have the same material. They could theoretically have different areas. They do, in fact, have different areas, but I'm going to say that both of them can be related to a single value. So the smaller one is 1/4 the bigger one. So this schematic diagram is not to scale, except in the fact that maybe it's a circle if you looked at it from the other direction. So 4 times A1 is equal to A2. And the question is, for this calculation, for this force P applied at this location, what is the eventual displacement at that point? Now, this is a deformable body, so we've got strain present in the left-hand side, we've got strain present in the right-hand side, and theoretically, since every atom is its own unit, these is theoretically an infinite number of degrees of freedom. However, it's not going to be quite that hard for reasons which I'll show you in a minute. Note also I've got here B, C, and D as locations. So B is at the left edge, C is at this interface, and D is at the right edge. These are locations, so we're going to have a displacement at B, which is going to be equal to 0. We're going to have a displacement at C, and we're going to have a displacement at D. Note I skipped A because I didn't want to have it be confused with this A. Okay, so we took this infinite degree of freedom system and have actually now made it into just a couple of degrees of freedom. UB, UC, and UD. Well, how do I know that? Because these are constant areas from here to here with a constant material property. If I know the displacement at B and I know the displacement at C, I can calculate the strain everywhere from one point to the next. And likewise, if I know C and D, I can calculate the strain everywhere there. So even though theoretically this is an infinite number of degrees of freedom in this problem, we can simplify that by writing strain and assuming it's constant over various regions. Okay, so this is just by definition of strain. The strain in region 1 is the change in length, that's UC minus UB, over the length. Now, in this case, that length happens to be 2L, right? Here's 2L. So the change in length, C minus B over 2L, that's the strain in segment 1. Of course, UB is also 0 because it's fixed at the left-hand side, so the total strain in segment 1 is UC over 2L. The strain in segment 2 is similar. Okay, it's change in length over length. We go back to the structure, so it's this location minus this location, the displacement's there, and you're dividing by the original length. In this case, the original length is L, so strain 2 is UD minus UC over L. All right, now the next thing we can do is we can write the strain energy. Keep in mind what we're doing is we're minimizing pi. Really what we're, so this is the minimum potential energy concept, which is very much related to that idea of virtual work, okay, mathematically quite similar. So this is U minus W or U plus V, depending on how you're describing. Is it a potential of the external loads or is it the external work? Either way, we can write it how we would choose to. Okay, so what is U? The first thing we need to now compute is U. This is the strain energy. And you remember the equation for strain energy was the integral of sigma d epsilon, then integrated over the volume. So in this case, we can say since the epsilons are a constant over the region, we can express the strain energy of any given region of this, any given substructure of this overall structure. It will be mathematically equal to 1/2 stress times strain times the volume. So in this case, the volume is A times L, capital A and capital L representing the areas and lengths of the segment, which we will then shortly turn into A itself and little l. Okay, so here again, recognizing that stress for a linear elastic problem is nothing more than strain times modulus. So that simplifies that equation a little bit. And what we see here is that we have strain squared. So this is 1/2 strain squared times E times A times L. The total strain energy is the sum of the two portions of the strain energy, these two different substructures. So we have strain energy here, we have strain energy here. The total strain energy is the sum of those. So now that's just 1/2 epsilon 1 squared times E1 times A1 times L1 plus epsilon 2 squared times E2 times A2 times L2. We now know each of these things, A2, L2, and E, and if we plug those in, we get that the total strain energy is 1/2 UC squared, UC over 2L squared times EA times 2L plus 1/2 UD minus UC over L, that quantity squared, times 4EAL. To alleviate any confusion that may have existed from prior in the semester, I'm using the dot symbol here to represent multiplication. It's not a dot product. And Nicole asks, where's the 1/2 come from? So that's a great question. It's quick enough to derive. So if I'm integrating a stress d-strain, I can then say that that's equal to modulus times strain d-strain, which then is going to be equal to 1/2 times modulus times strain squared. Okay, so that's where the 1/2 comes from. And this is very similar, for your entire engineering life, when you talked about energies, it's always in this form of 1/2 times some stiffness times some measure of displacement squared. Spring energy is 1/2 kx squared. You've seen that a million times. this is very much just a generalization of that idea. Okay, so that's pretty straightforward. Now, we can also then do the external work, or also called the potential of the external loads. So the external work would be equal, if we go and look at this, the external work is P, this force, times the displacement at this location, UD. That is the amount of external work. That's positive. If we're going to write it in terms of the potential of the external loads, we have a negative sign that gets added to that. So we have V is equal to minus P times the displacement at D. And the total potential energy now is just the sum of these two things. Okay. The end result is, remember what we're doing here is we're now taking the variation of pi, which in this case has degrees of freedom UC and UD. And this is going to end up being d pi duc times delta UC plus d pi dud times delta ud. And that's going to be equal to 0. And then, of course, we had to recognize that this term is arbitrary and this term is arbitrary. We cannot use this term to cancel that term and vice versa. So what do we know? We know this term has to be equal to 0. And we know this term has to be equal to 0. So this term here is now written here. And, again, I feel this is a little clumsy trying to do it with the presentation format instead of on the board, but I'm doing my best here. If this is confusing, stop me and we can go back and readdress some of these issues. But anyway, so we're calculating the partial derivative of pi with respect to the displacement at UC, and we know that that has to be equal to 0 if and when equilibrium is occurring. So what do we know? Well, we know U, that's this one up here. We know V, that's this one here. We can take the derivative with respect to UC. So here up at the top, this becomes 2UC times EA over 4L. And then we end up with a 2 UD minus UC. And then we pull a minus 1 out of here. So that ends up being right here. That, of course, multiplied by 2 EA over L. Okay, so this is d pi duc. If we're looking at the external work, we take its derivative with respect to UC. It's going to be equal to 0 because there is no external work being done at UC. It's only being done at UD. So this entire derivative is now written here. Okay, similarly, we can now take the derivative of pi, that is u plus v, with respect to d, or I should say ud, the displacement d. So if we go up here again, if we look at this first term, there are no uds in there, so its derivative with respect to ud goes to 0. And what ends up here, we're going to get a 2 times ud minus uc. And that is what ends up here, times, of course, 2EA over L. So that's what ends up here. And then last but not least, of course, we take the derivative of this potential of the external loads with respect to UD, and what remains after that is minus P. So we now have two equations, this one here and this one here. How many unknowns do we have? We have 2. So we have 2 equations and 2 unknowns. As long as these equations are independent of each other, we can solve for the unknowns. Okay, that's really can be done any number of ways. You guys can solve for two equations with two unknowns all day long. I'm just going to do it very quickly. I'll do it first by adding the two equations. Of course, the right-hand side is going to be equal to 0. And then when we do that, we cancel some terms out, and we can then compute that UC is equal to P times 2L over EA. And we can do, well, let's see here. The second equation then is here. And we can use that equation plus our knowledge of the magnitude of UC to actually solve for UD. And so that really ends up here. And in terms of capital L, so to understand where capital L comes into this thing, oh, I forget. I guess I didn't define capital L very well here, but if I remember correctly, little l is capital L. Anyway, bottom line, we can, or no, I got to step back from my prior statement. The whole thing from here to here is length L. So if we look at the displacement at these two locations, we get that the displacement at C is 2L over 3EA times P. We get the displacement at UD as 3 times PL over 4EA. Okay, so again, what have we done? If we go back and take a big picture view of this, we recognize that we took really an infinite number of degrees of freedom. We tried to minimize it down to the minimum number of degrees of freedom necessary to describe the strain everywhere. For this problem, it happened to be 2 degrees of freedom was sufficient to describe the strain everywhere. Then we wrote the total potential energy of the system. We took the variation of that. That's the derivative of the functions of functions, and set that equal to 0. So we're, mathematically minimizing. That's extremization. You guys have done derivatives and set them equal to 0 for a long time. You always called it a maximum or a minimum. So in this case, we're really minimizing the total potential energy of the system. And from that, knowing the independence of the degrees of freedom, we can calculate the actual displacement fields. All right, so that's the summary. I'm going to pause for a minute. I anticipate there's probably still some confusion out there. Really, I'm a little concerned, as I've said a couple times, about how this presents on the slides rather than going through and doing it mathematically with you. So I'll pause for questions. Any questions out there?
Yeah, I have a question. So
yeah,
for
go ahead.
your UD, is that displacement like measured relative to point B?
No, UD, so that's a great question. You could define a relative displacement if you wanted to, but in this case, it's an absolute displacement.
Okay.
And how do we know that? That's because of the way I define strain. Okay. So here I define strain as the change in length, which was UD minus UC. Okay, so in this statement here, we're stating that this is an absolute displacement and this is an absolute displacement. Now, there would really have been no problem. We could have put a different relative displacement term in here, and then we'd have still 2 degrees of freedom. We'd have the initial degree of freedom and the relative degree of freedom. The magnitude, of course, would compute to be a little bit different than what we've computed. But it's, I would say, as a general rule, a good idea to use absolute degrees of freedom, unless you have a compelling reason to do something else.
Okay, thank you.
Okay, so I'm not seeing any further questions. We have about 10 minutes left, so I'm going to go ahead and start the next lecture as we're running a little low on time. Let's see here, where'd it go? Lecture 25. Okay. Now, I think if there's one more takeaway that I want you guys to take away from the class is this idea of we can approximate solutions to problems rather than calculate them exactly. And this framework that we've now introduced over the last 2 or so lectures, this idea of virtual work and this idea of minimizing the total potential energy, these tools that we have in place now provide a mechanism by which we can do very advanced analysis techniques. And one of those is what you're working on for your project. So the finite element method, believe it or not, has been the foundation for that has been described now over the last lecture and a half. To actually understand that mechanism, though, we need to go through and calculate what we're going to call approximate solutions. And the first one we're going to deal with is the so-called Rayleigh-Ritz method. And we're going to apply the principle of minimum potential energy, and we're going to use it to obtain an approximate solution. Now, I hope to help you understand that over the next 10 minutes. Now, how is this different from the exact solution? Okay, so what's different between an approximate solution and an exact solution? Let me see if I might have a good, yeah, this is where things don't translate as well when we're doing the lectures these ways, okay, rather than doing it on the board. Okay, so let's say that we have a structure. Maybe that structure begins to look like an axially loaded structure. So the left-hand side is fixed. The right-hand side, or I should say the structure maybe looks like this. Okay, obviously we have a structure. It's thicker over here and thinner over here. We're going to have an approximate strain over here that is large. If I were to plot the displacement field of this structure, and I were to put the displacement field, so the u in the x direction as a function of x position, where x is measured from here, the displacement is going to be 0 at the left edge. It's going to increase slowly at first because that's a thicker section, and then it increases faster as we get to the end. So it starts to look something like that. Now, when we're solving approximate solutions, we're saying, well, we're engineers, we're not physicists. We're not particle physicists. We don't need something to be precise to, 10 or 20 digits. We need it to be, within a few percent most of the time. And so this structure that I've drawn may actually be very difficult to analyze because it's got a continuously varying structure. But we could, for example, approximate this structure as one that looks more like this, with 2 constant cross sections. Or for that matter, we could approximate it as looking just like a single cross section. Okay, so here's 1 and here's 2. Now, if we actually then calculated the deflection, We would like it to look something like this. So for the single, for a number 1 up here at the top, we would want it to be pretty close to our other solution. Let me go ahead and draw one on here. We'd like it to look something like that. And the reason why I say I want it to look something like that is we would like to sort of minimize the overall error that's present. And so I would say that kind of missing a little bit on this side and missing a little bit on this side. This is not a technical description. We'll get into more technical descriptions in a little while. But this is probably a reasonable approximate solution for this one. And let's say if we're willing to accept, 25, 30% error, we probably have nailed it. It's good enough. Okay, if we wanted to do 2, we could then instead say, all right, well, I would want one that kind of looks like this, which is then attached to one that kind of looks like this. And I know these don't draw very well. It's tough to draw with a mouse, but you get the general idea. If I divide it into 2 discrete sections, I can get an answer that's closer than the one that was only 1 discrete section. We minimize the overall error in comparison to the other one, and we get, in fact, for this particular problem, very close to the actual displacement field. It still is not the same, but it's close. It's an approximate solution. And for much of engineering, approximate solutions are perfectly acceptable. Okay, now that was an informal description. We need to put some formalism to this. We need to come up with a way of quantifying, in some sense, the amount of error that's present. And then if it's quantifiable, we then need to minimize it subject to the restrictions that we're putting on or the assumptions that we make. So that is the very foundation of this idea called the Rayleigh-Ritz method. We're going to use the principle of minimum potential energy as our metric of the goodness of our approximate solution. Now, how do we do it? What we do is we describe, now going back to this, did I delete that? Oh, shoot. I hope I didn't delete it. Well, what I'm going to do is I'm going to take this solution here and I'm going to make some assumed solutions. And for example, if we had a linear one, I'm going to describe a displacement field with something that we will eventually call a Rayleigh-Ritz function or a shape function. So our approximate field follows this given shape. In this case, it's linear. Okay, so we're going to describe our displacement field. We're going to assume it, really. We're assuming what it looks like, and we're going to describe it as a shape function. And then ultimately, we're going to determine some coefficients that optimize that shape function. So this is not something that we can do entirely arbitrarily. We have to follow some rules. The first rule that we have to follow is that this is an admissible function. It needs to satisfy the so-called essential boundary conditions of compatibility. These, by the way, are called geometric boundary conditions in some places. If I look at this example problem that I was referring to, here at the left edge where we had a constraint, I can't violate the constraint. Okay, that's what these words mean. It needs to be admissible. Again, we're going to put mathematical terms on this. We're going to wrap this in math over the next lecture, but conceptually, that's what we're doing. And what we're now doing, what we're functionally doing, is we're taking this infinite degree of freedom problem. We have this problem where the structure had this weird sort of geometry to it with an infinite number of degrees of freedom. There's theoretically at each atom or even subatomic particle, there's a unique displacement field. Of course, subatomic particles are constantly vibrating, so that's not the best. We don't want to take it that far, but theoretically, at every small differential volume has a different differential displacement, infinite number of degrees of freedom, and we're going to now describe that set of degrees of freedom by an approximate solution that maybe only has 1 degree of freedom. So in this particular problem, if we know the value of the displacement here, and we are saying it is a linear interpolation from there down to 0, we're describing the entire infinite degree of freedom system as having only 1 degree of freedom. So that's what this means. Replace an infinite degree of freedom problem with an approximate problem that has finite degrees of freedom. Now, there are some mathematical requirements. We'll go into them in more detail in the advanced structural mechanics class, but one of the things we need to know is we can't skip essential energy terms. This is called completeness. That's the mathematical description of that. We're not going to really get into the details of it here in this class very much, but I put it up there so you know that this is something that is required. Okay, in the end, the solution that we're proposing takes a form. In this case, the form, most often these are going to be polynomial equations, so this is just a general description of a polynomial equation. Or really, it does not have to be polynomial equations, could be other equations as well. So what we have is that our displacement field is going to be the sum of some coefficients, unknown coefficients, degrees of freedom, times some shape function. The shape function could, in theory, be a function of position x, y, and z. Like in the drawing that I gave you, it was a linear function of x. So it would be something like that. So in these terms, the displacement functions ui, vi, and wi, these are assumed. We're assuming a linear displacement field as an example. They must be admissible. They cannot violate boundary conditions. The coefficients, that's these magnitudes here, are unknown and are what are to be determined. And so what we're ultimately saying is we initially don't know what this value is, the magnitude of the displacement to the right-hand side, but we do know that if we can compute that using some principle, that we now have a pretty good solution. That principle will be the minimum potential energy principle. Okay, so those are the unknowns of the problem. And ultimately, the total potential energy then becomes expressed in terms of these variables, these degrees of freedom, these things that we still have time to find. So in the end, we express the total potential energy, which we now are calling U plus V. It's going to be a function of those coefficients A, B, and C. Then we will minimize with respect to those A, B, and C's, and we'll get a series of equations, one for each unknown. Because these are independent and arbitrary values, one for each unknown, we'll have 3 equations for 3 unknowns as an example. Okay. The last statement I'll make for the day, and then we'll break until next week, is to say that when we make an assumption on the displacement field, if by making that assumption we don't actually admit the actual displacement, we're imposing a constraint on the computed displacement. Let me go back to my diagram. Okay. If this curved field was the real field, and I am going to state, I'm assuming it's a linear response, then the best calculation I'll ever get is a linear calculation, and I'm constraining the displacement field to be linear in my calculation. It is not real, therefore it is an artificial constraint in some sense. So again, the solution won't be exact, but hopefully it'll be close enough. It'll be a good approximate solution where we can define good. Okay, so that's a great place to stop for the day. My monitoring machine has been stable here for a little while. I'm not seeing any questions in the chat window, but I'm happy to take questions. Now from you guys, I'll hang out here for a few minutes. for sure. Certainly, we can also discuss a few things about your projects. If you have quick questions about those that can be addressed in just a couple minutes, we could do that now as well. And for those of you who are leaving, I will see you guys on next Tuesday.